Hey everybody. So continuing from the last class where we had discussion regarding image formation by spherical mirrors. Now it doesn't seem to be a good idea to every time draw the diagrams to see where the location of the image is, and when you keep the object at a certain distance. We need some mathematical analysis, some mathematical formula that without drawing the diagrams we get to know where the object is kept, then where the image would be formed. That mathematical analysis we can have using two major formulas in optics. One is mirror formula, other is magnification. That is what we will going to cover in today's class. So mirror formula and magnification formula. Before we jump into this, we must understand some of the terminologies of the spherical mirror, which although I've already discussed, but once again, focus is the point where the parallel rays coming to the axis finally converge. So the distance of focus from the pole is defined as the focal length. So as you can see in the diagram, this F, that's the focal length. And when you talk about the center, the distance of the center, then its distance is defined as the radius of curvature. I'll point it out here. So here you saw the focal length from pole to the focus. Then you can see the center. So unfortunately in this diagram it's not represented, but you can imagine somewhere here the center would lie. And so the distance from pole to center would be radius of curvature. Now two different distances that are also important is one of the object, where the object is kept. Everything is measured right away from the pole. So you can see object's distance is represented by U, and it's measured all the way from the pole to this point where the object is kept. That's U. Then we talk about V, that is the image distance. You see, here is the image formed. That is also from pole to image, that is V. All right. So these are a few important terms that you need to remember. U is object distance, V is image distance, F is focal length, R is radius of curvature, all measured from pole only. Pole is like origin in coordinate axis. All the measurements you will do must always be from the pole itself. So after knowing these terminologies, it's time that we move ahead. First of all, focal length and radius of curvature, you don't need to again and again, remember both of them or use both of them. Actually, there exists a relation between them, which makes it very easy to use only one of them. And what that relation is simply focal length is half of the radius of curvature. That is a relation. Now, how do we know this? How do we prove this? So do you see a diagram here? I've drawn a diagram here where parallel rays are coming, and you can say they are getting focused at the focus, like here. That's how focus is defined. And then what you see as the dotted line is the normal for this reflection. So incident angle must be equal to the reflection angle, which you see here, theta. And if that is the case, then you can also see by alternate interior angles, this theta must also be equal to this theta. Alternate interior angles, everybody can see a Z is getting formed. So that's how the other angle is also theta. And if these two angles are theta, then we know that it is an isosceles triangle. Which triangle? Triangle CFP prime. It's an isosceles triangle. So what must be there? Well, FC must be equal to FP prime. These two sides must be equal. Correct? Now, we need to understand that in all the cases of optics we will be doing of this chapter, all the rays are actually paraxial rays. What is meant by paraxial rays? Paraxial rays are the one which are very close to the principal axis. So this ray which you see over here, this BP prime, it is actually very close to the principal axis. While drawing, we draw it so much far away, but actually it is very close. And so if the ray is very close, then P prime and P are also very close to each other. P and P prime are very close to each other. And if that is the case, then I can write one more thing, and that is Fp prime is equal to Fp, because they are both very close to each other. All right. And if that is the case, you can clearly see Fp prime here, Fp prime here. This gives us a relation that Fc is equal to Fp. One important result we have obtained, isn't it? And after we know that Fc is equal to Fp, we quickly realize that Fp is nothing but the focal length, like this. And since Fp is equal to Fc, then Fc must also be focal length, isn't it? That's what we have here. Fc equal Fp, both are focal length only. But then we realize the distance from P to C is all the way the radius of curvature. And if that is radius of curvature, then we got our relation that R is 2F. Or to write it the other way, F is R by 2. So hence proved that focal length is half the radius of curvature. So this result you should now keep in your mind. And also the important thing that will be there in every question we will be doing later, every concept we'll be learning later, and that is paraxial rays. Rays are very near to the principal axis. So now moving ahead, the mirror and magnification formula that I am talking about. First of all, I represent to you what are they. So mirror formula relates image distance, object distance, and focal length, as you can see. This is how they are related. And what about magnification? Well, magnification is simply how the object is by how much times enlarged or how much times diminished. That's how we define it. So let's say I tell you object is h height and image formed was 2h. So we said double magnification. It's like you use the word magnification in camera also, magnify the image. So basically it simply means how much times larger is image compared to object. So magnification can simply be put as the image height over the object height, as what you see here. That's magnification. Later on, we will prove that how it comes out to be negative V by U. All right, so magnification can be written as both. Negative V by U is I by O, and that's how magnification is defined. And there we have our very own mirror formula. These two formula will be very much useful in every question that we'll be doing. So let's begin with the derivation then. The first derivation we must have is of the mirror formula. All right. So let's begin with that. Now I need some space, so let me quickly add some of the slides here. So little patience, I'm just all right. So I'm done adding the image. Let's now deal with mirror formula. So again, I repeat, what we are actually about to do is the derivation of the mirror formula. So let's begin with the object placed beyond the center. So what will be object distance? Well, this will be the object distance, u, all the way measured from the pole. This is the image. So this is our object and this is the image. So that's the image distance. You can see all the measurements are being done from this pole only. That's like our origin. All right, this is the focal length, as we already know. Let's look at few triangles here. I may name this point as A and this point as B. This point as D. So let's begin. First of all, I would like you all to look into the triangles AOF and FDP. These two triangles you will find to be similar. Why? Because this is vertically opposite angles. They are equal. This angle is 90 degree. And here I can drop a perpendicular that is also 90 degrees. So by angle-angle properties, these two triangles are similar. Now what is this perpendicular that I have dropped? That is same as the image height, isn't it? That is what I called as the image height. And this is what I'm calling as object height, O. So this perpendicular distance is also O. And now I can simply apply the similar triangles property. And what is that property? First of all, let's take the ratio of perpendiculars. Perpendicular of triangle AOF is O. Perpendicular of triangle FDP is I. So I'm sorry, this has to be I, not O. Image distance. And that must be equal to the ratio of their base. Ratio of the base of triangle AOF. AOF base is OF distance. What is OF distance now here? You can see this is all the way U and this is F. So what we need here is actually U minus F as the base of that triangle. So U minus F over what is the base of triangle FTP? Now again understand, you might say there is a little difference, but again we use the property of paraxial rays. Point D is very close to point P. And if that is the case, then this focal length itself represents the base of the triangle, F only. Now let's look at the triangle. This I will name as E. Now the two triangles I want you to look at is BIF and the triangle EFP. Again, I will drop a perpendicular and this height, the perpendicular I have dropped, has to be the object. These two triangles are also similar. Again, it is the same property, 90 degrees, vertically opposite angles. And so in that also, I can equate the perpendiculars O by I and base. Base of triangle EFP, again, it should be focal length. And what about the base of triangle BIF? So if you closely watch this distance, it is V minus F. So from equation number 1 and 2, their LHS is same, so should be their RHS. Let's equate their RHS. So U minus F by F is equal to F by V minus F. Cross multiply. F square gets cancelled. And then you can send the terms on the other side. And now what I'll do is I will divide by UV into F. All right. and see what we are getting. So I'm getting 1 by f minus 1 by v equals 1 by u. And so rearranging, we will get the famous mirror formula, which is what I gave you at the start. So this is how the mirror formula is easily proved. All right. How would one going to prove the magnification formula? Well, we can use either one of them, either equation number 1 or equation number 2. Any one of it you can use and simply prove the magnification formula. Let me show that to you as well. Let me just quickly add a slide for that as well. All right. So I pick up the equation number 1 itself. This is the equation number 1. Let's reciprocate this. The moment I take the reciprocal, I realize image height by object height is how we define the magnification. How much bigger is image compared to object, isn't it? That's what we define it as. Now, here what can I do? Well, I can just simply divide by focal length. That focal length I'm sending in the denominator. U by f minus 1. Now here you have u into 1 by f. And what is 1 by f? From mirror formula just now we learned 1 by v plus 1 by u. And then we realize when you multiply u inside, 1 and 1 will get cancelled, and finally you will receive v by u, isn't it? But this is not our final answer. Why is it not the final answer? Because now we would have to use sign convention here. Our formula should be independent of the particular case which we are deriving for. It should be a generalized formula. So when you look at the diagram that we took, you can see both object and image are on the left side. And you also notice object is erect, image is inverted. So let me show here. This is how our ray diagram is. This is our object. This is where the image is. So you can clearly observe both the object distance, u is negative, and even the v is negative. Why it is negative? Because we follow the simple sign convention of coordinate axis. How do you see coordinate axis? You see this is the positive y-axis, so anything that is measured up is positive. You see this is negative y-axis, so anything that is measured down is negative. This is the positive x-axis, so anything measured to the right is positive. And this is negative x-axis, so anything that is measured towards the left is again negative. So that simple sign convention we follow in mirrors also. The moment you see that u and v are being measured towards the left only, you immediately realize they are negative. And then you look at object and image height. Object height is measured up, but look at the image height, that's measured down, isn't it? So this sign convention I must apply in my derivation. So I got I by O, I should actually be negative, object should be positive. When we talk about V here, V should be negative, and even the U, because even that is negative. And from here, what we realize is that I by O, the magnification, is actually negative V by U. And that's our magnification. So that's how we derive the magnification formula. So it is very important that you remember the sign convention even while solving the question, You must keep in mind whether the object is towards the left, then it has to be negative. Whether the image is formed to the left or right. If image is formed on the left side, it should be negative. If it's a virtual image which is behind the mirror, then you will be measuring it to the right, so it will be positive. So all these sign conventions are very important. So let's move ahead with the first question that we have. So every time you should draw a diagram of what they are saying. So question says an object 2 centimeter in size is placed 30 centimeter in front of a concave mirror. So this is our concave mirror. The object is 2 centimeter height. You can see focal length is 15. An object is placed at 30 centimeter, which is at center. Its height is 2 centimeter and it is placed at 30 centimeter distance. At what distance from the mirror should a screen be placed in order to obtain a sharp image? So where should I keep the object, the screen, to obtain a sharp image? Well, this is very easy because in this case we realize that focal length is 15 and if object is kept at 30 centimeter, then it is placed at the center. And you remember from the ray diagram that when the object is kept at the center, the image forms at the center itself, isn't it? So what should be our answer? Our answer should be screen should also be placed at the center only, at 30 centimeter distance only. So our answer is 30 centimeter. How can we get the same thing from the formula? It will be a very good verification. So I apply the formula 1 by f equal 1 by v. Suppose we want to find where the image is forming. Plus 1 by u. And what is the object distance? Well, object is towards the left. So first I will write the entire formula. Now 1 by f. How is the focal length of a concave mirror? It's to the left side. Do you see in the diagram? 15 is to the left. So negative 15. 1 by v plus 1 by u. Object distance is also to the left. Negative 30. And when you see that, you will obtain v as negative 30 centimeter only. So formula gives you the same answer, isn't it? Moving ahead. An object of length 2.5 centimeter is placed at a distance 1.5 f from a concave mirror. Again, a concave mirror. Object is placed at 1.5 f. If this is f, then somewhere here the object is placed and its height is 2.5. So our object distance is 1.5 f. So you can, as a matter of fact, write at the start of question, u is to the left, so negative 1.5 f. It's a concave mirror, so focal length is also negative. All right. The length of the object is perpendicular. Find the length of the image. They're asking us what would be the image height. So simply use the mirror formula. 1 by negative f, remember it's a concave, equals 1 by v plus 1 by u. U is negative 1.5 f. So what answer will this going to give you? Negative 1 by f plus, that is 2 by 3f equals 1 by v. So what answer is it giving you? So take the LCM, solve it. You will going to have negative 3 plus 2, that's negative 1. So negative 3f, isn't it? Negative 3f is the value of v. So image is also forming to the left side. That is what this answer tells you. But they asked us the image length. How do we get the image length? From magnification. Magnification is I by O, and that is equal to negative V by U. In this case, V is, so negative is already there, and V is negative 3f, and U is negative 1.5 f. So what do we realize here? I by O is negative 2. So image length is negative 2 times object length. That is negative 2.5 into 2. That is 5 centimeter. And since image length is coming out to be negative, that means image is forming in the downward sense. That's why it's negative. So image is inverted. Next question. A 2 centimeter high object placed on the principal axis of a concave mirror at a distance of 12. So U is given to us, negative 12. And then they give and also object height is given. Object height is 2 centimeter, positive. If the image is inverted, now they're saying image formed is inverted. So first of all, it will be measured downward, negative height. It's real and it's 5 centimeter high. So image height, when I write, I should not take it as plus 5. It's downward facing, so I must take it as negative 5 centimeter. Find the location of image and focal length of the mirror, right? So location of the image means V, they're asking. So V can be easily found out using the mirror formula. 1 by F. Sorry, first we need to apply here the mirror formula. Let's simply use, have they given us the focal length? No, even the focal length is not given to us, but we can use the magnification formula for sure. What is magnification formula? I by O is negative V by U. So just apply that. And what do you realize? It tells us image height, which is 5, object height, which is 2, is equal to negative V, which we need to find out, and U is negative 12. And so first thing is we obtain the image distance, and that is negative 30 centimeter. So first part is obtained from the magnification formula. For the next part, we will use the simply mirror formula. 1 by F is 1 by V plus 1 by U. U is negative 12. So what would this give you? F will be negative 60 by 7 centimeter. So you realize how using mirror formula is so easy. You just have to keep one thing in mind, and that is sign conventions. They are very important. All right. So that's it for the day. See you in the next lecture.